If you use machines with motors, then it's important that you know the fundamentals of motor selection. It may be that you seldom have to do any actual selecting because machinery manufacturers usually either supply a motor they know will do a job best or specify the exact type and size to use. Yet if you use motors in any way, it's important to know the fundamental steps that lead to the selection of the proper motor. With your car, for instance, you don't decide the type of pistons in the engine or the oil pump used, but you should know about these things in order to get the most out of your car and keep it in working shape. Suppose a machine needs a 5-horsepower motor. There are over 1,000 standard or semi-standard 5-horsepower motors that are candidates for the job. Maybe several of these motors are suitable, yet in long-range terms of cost, operation, maintenance, and safety, there's usually one that's best for the job. Let's see, then, just what's involved in choosing the right motor for a machine. Let's take a close look at the 5 basic steps usually followed in motor selection. Study the driven machine, determine the motor horsepower, determine the electrical characteristics, determine the control equipment, and determine the mechanical design features required. It's logical, of course, that the driven machine should be studied first, because this shows what the motor must do. A tailor, for example, would never start cutting cloth for a suit without first taking measurements, and so all characteristics of the machine should be determined in order to choose a motor that will fit. Take reliability, for instance. With a device such as this, which opens and closes theater curtains, the chances of a motor failure are small. Yet, if it should happen, the curtains can always be opened and closed by hand, so reliability is mainly a matter of convenience. On this coal conveyor, however, which is one link in a continuous manufacturing process, a motor breakdown involves an economic loss, and reliability is all important. Here, special equipment is justified if it adds to motor reliability. In addition to purpose, the load and speed requirements of the machine must be known, for this shows what torque and speed the motor must have. From the duty cycle of this compressor, for instance, its steady speed of operation indicates that a constant speed motor is needed, while the load carried shows what horsepower and running torque the motor must have to carry the load. In addition, when it's known whether the compressor starts loaded or unloaded, then the starting torque can be determined. Also, the frequency of starting and the time it runs continuously show the time rating the motor should have. Generally, a machine's duty cycle fits one of 4 load and speed combinations. The first, where speed is constant and the load nearly constant, is characteristic of most fans, pumps, and compressors. A second combination, where speed remains constant but the load is variable, is found on a dough mixer such as this, on winders, and on certain machine tools. You see a third combination in this film coating machine, which operates over a wide speed range with a load which is either constant or variable with the speed. A fourth combination, where the load is either constant or variable at full speed, is found on machines such as this laundry extractor, which must start and stop frequently. After the machine's duty cycle has been determined, it's important to consider the product or process involved. On a textile loom such as this, a totally enclosed motor would be used because lint would soon clog up a motor with an ordinary open-type enclosure. It's important, too, to know if the motor will operate in a hazardous location, such as in this mine or in some refineries. Here, an explosion-proof enclosure is specified for safety's sake. With any application, reasonable motor life can be assured if the motor is placed away from liquids or dirt, as in this paper mill, so that proper ventilation is assured. After the driven machine is studied, and its purpose, its load and speed requirements, its duty cycle, and the product or process involved is known, the motor horsepower must be determined. In most cases, machinery manufacturers have compiled tables showing the horsepower required for their machines, determined through the use of various horsepower formulas. One method is by well-known mechanical formulas found in engineering handbooks or in any text on mechanics. With a hoist, for instance, if the weight of the load is known, the speed of hoisting, and the mechanical efficiency from the load to the motor shaft, then through mechanical formulas, the motor horsepower needed at the shaft to hoist the load can be determined. Other mechanical formulas have been compiled to determine the horsepower required for compressors and electric drills and for lathes, punch presses, and the like. In some cases, the motor horsepower is determined by so-called experience formulas, such as the one in this fan manufacturer's handbook, which shows what motor horsepower is needed for a certain set of conditions. In developing these formulas, manufacturers run tests on motors driving many machines of the same type, and from the information gathered, they compile general formulas. With a conveyor, such as this, experience formulas can be used to see what horsepower is needed to power the empty conveyor, to convey the material horizontally, and to either raise or lower the material by the conveyor. As a rule, these experience formulas can be applied to conveyors of all types, where friction losses pose a problem, and to machines which cut, form, and roll metal, such as this bearing-making machine. With some machines, it's necessary to use a combination of these formulas in determining horsepower, especially where changes in load and speed make it hard to outline a definite duty cycle. With a punch press, for instance, the peak load on the workstroke can be determined by mechanical or experience formulas. However, the power required to drive the inertial load of the flywheel, which varies with the change in speed required and the time between strokes, often must be calculated from special formulas found in engineering handbooks. On a punch press like this, and on many other industrial machines, this inertial load is the factor which actually determines the horsepower. Where the process is new or untried, often the motor horsepower must be determined by trial or testing. One method is to apply a motor somewhat oversized and then measure it under typical load conditions. At other times, the horsepower can be determined simply by comparing the new process with machines doing work of a similar nature. On some new process drives, the approximate horsepower may have to be calculated from assumed load data, such as friction and inertia, and then a trial motor tested on the machine for suitability. In replacing a motor, data from the old motor nameplate can be used, provided any changes that have been made are taken into consideration and that operating characteristics of a new motor of that type will do the same job. If there's any doubt, however, it's wise to recheck the application and run a load test if this can be done. One check is to measure the motor speed under normal load with a tachometer or speed indicator. If the actual full load speed is lower than the rated full load speed, there's a good chance the motor is running overloaded. Another check is to measure the current flow. A hook-on voltammeter placed around one of the motor leads shows immediately whether or not the current flow is within the limits specified on the motor nameplate. If either check shows a need for a larger replacement motor, then the motor horsepower can be determined through the use of either mechanical formulas, experience formulas, a combination of the two, or by trial or testing. When the horsepower needed is known, then it's necessary to determine the electrical characteristics required in driving the machine. From the standpoint of the user, it's always good policy to first contact an electric utility representative in the area. For one thing, he can tell if the capacity of the service entrance or plant wiring system is sufficient to handle the new horsepower load, or whether new feeders, fuses, switchgear, or substations are necessary. At the same time, he can tell whether or not the electric utility must add new facilities to handle the new load. If so, this takes time, and if not considered until the last minute, it may hold up the installation. A second reason for checking the utility is to make sure the new motor load won't cause voltage fluctuations or a low voltage condition. Voltage fluctuations are the cause of light flicker, which occurs not only in the plant where the motor operates, but in others as well. Before the motor is chosen, of course, the service characteristics available should be known. This means determining the voltage and whether direct current or alternating current is available. In most cases, AC is supplied, so the phase and frequency must be checked. Service voltages vary, but the utility representative can tell what is available. With alternating current, homes, many farms, and small commercial shops generally are wired for single-phase power, while most industrial plants are supplied with polyphase power. Small single-phase motors operate on lighting circuits, and in order to avoid light flicker, those which start on full voltage are restricted to about 5 horsepower, or in some cases to as low as 1 horsepower. The standard AC frequency is 60 cycles in most cases, so most motors are designed to operate at that frequency. When the voltage, phase, and frequency of the power supply have been determined, then motor manufacturers' catalogs show the speed and torque and exact horsepower range of motors which operate on the power supply at hand. Obviously, it's desirable from the standpoint of cost, delivery, and renewal parts to use standard motors if possible, rather than special equipment. For a lower cost, these motors provide standard speeds which meet most job requirements. With 60 cycle power, standard AC synchronous speeds can be obtained ranging from 3,600 to as low as 80 revolutions per minute. This partial list shows some of the fixed speeds available, each determined by the number of poles of the motor. With small and medium motors, 1,800 RPM is the most popular speed rating. Below 720 RPM, squirrel cage motors are not normally used, even though available, because gear motors or synchronous motors are more efficient and less costly at low speed ratings. Where a direct current motor is required and only AC power is available, then power conversion equipment is necessary, but often the better control and greater flexibility of a DC motor more than makes up the extra cost. Standard DC motor speeds are similar to AC full load speeds, but almost any speed within reason can be obtained. On a rubber winding roll, for instance, where the machine must be threaded slowly and then operated at high speed for winding, a DC motor system can be obtained to run at a speed range of 100 to 1, or even higher. With any application, the nominal supply system voltage generally is higher than the motor nameplate voltage to allow for slight voltage drops along the line. 440-volt motors, for instance, are designed to operate on nominal 480-volt supply systems. Now, let's pause a minute and review again the steps in motor selection while the operator changes the record. When a machinery manufacturer chooses a motor, selection of the proper speed often hinges on a question of overall economics for both motor and machine, particularly on grinders, pumps, fans, and other machines which run at constant speed. On a pump, for instance, which runs at a constant speed of 1,800 revolutions per minute, a direct connected 1,800 RPM motor can be used, thus greatly simplifying the drive. On a machine such as this cement mixer, however, which runs at a speed slower than standard motors, it's good practice to make a cost comparison between a low-speed direct connected motor and a high-speed motor with some form of speed reducer. Before final selection of a motor, the application always should be checked to make sure the electrical characteristics of the motor suit the load of the driven machine. In other words, the motor should provide the torque needed to start, accelerate, and pull the load during the machine's cycle of operation. In addition, the motor rating should be sufficient to avoid overheating during its required period of duty. Here's how this point is judged. Whenever a machine operates at full load for more than an hour, it should be continuous rated, designed so that heating resulting from normal load won't cause the temperature of any part of the motor to exceed its rated temperature rise as shown on the nameplate. Pumps and fans, for instance, usually need a continuous rated motor, as do compressors, conveyors, and other machines which run at full load for long periods of time. Not all machines, of course, do run continuously at rated load, and when this is the case, it may be that the motor can be intermittent rated. In other words, rated on a short time basis. This cylindrical grinder, for instance, may run for long periods, but only for a short time at full load. By checking its load and time cycle, calculation will show that its operation requires an equivalent of only 15 minutes operation at full load per hour. Therefore, a 15-minute intermittent rated motor at the horsepower required would be used. When replacing a motor or selecting a motor for a new machine, it always pays to check the conclusions with the manufacturer of the machine, particularly as to operation under new or changed conditions. In addition to checking the suitability of the motor for the machine, in many cases he can help in determining the control equipment needed. In its simplest form, control must always be provided to start and stop the motor, protect the machine and motor from damage, ensure the safety of the operator, and meet the starting requirements of the machine. For a machine like this handkerchief ironer, where the load is non-reversing, probably a simple switch to throw the motor across the line is all that's needed. On the other hand, a cold strip steel mill requires this elaborate combination of magnetic control devices, electronic equipment, amplidynes, and motor generator sets, so the equipment can operate over a wide speed range with precision control at any point. By and large, however, fairly simple control will handle most drives, and this is available from standard general-purpose listings. Through its construction and operation, control can be separated into two broad types, manual and magnetic. As the name implies, manual control includes electrical contacts which are opened and closed manually through the use of a convenient lever or a toggle mechanism. This type of control is well suited for small applications such as textile looms, conveyors, pumps, and other machines where the control operates infrequently and can be located within sight of the motor. Magnetic control, on the other hand, requires push buttons or other control circuit switches which energize electromagnets to open or close electrical contacts. This type of control is better suited for larger applications and where more frequent operation is needed. Magnetic control is the type used, too, with machines like this automatic welder, where it's desirable to operate the machine at a point away from the process. Remote control, such as this, can be accomplished with such control circuit devices as float switches, pressure switches, time switches, and thermostats. With any job, control can provide electrical protection for the motor through overload protection, which every motor needs, under-voltage protection, which should be specified when needed, and short-circuit protection. On this drill press, for example, if too great a load is applied, the control automatically disconnects the motor so that an overload won't damage the motor. Generally, motors are designed to allow for small voltage variations. Yet, if there's a chance the supply voltage might fall below a proper operating level or fail entirely, under-voltage protection should be provided to open up the circuit and prevent restarting without positive action by the operator. With any application, the National Electrical Code states that short-circuit protection must be provided by fuses or circuit breakers for both the control and the branch circuit supplying the motor. Often it's more convenient to obtain short circuit protection for the controller itself in the same control unit which provides electrical protection and operating features rather than in a separate unit. Modern controllers provide mechanical protection which safeguards the operator from shocks and burns. All live parts are enclosed in metal. If the control is exposed to weather, water, dust, or if it must operate in a hazardous location, then a special enclosure to meet these conditions must be specified. In selecting control, its horsepower and voltage should always correspond with the horsepower and voltage of the motor to be controlled. Many times, of course, it's not necessary to select control because it's built in by the machinery manufacturer or provided by a dealer or contractor at the installation. Control can be used to greatly increase the flexibility of many machines. With special control, for instance, this hosiery knitting machine automatically operates part of the time at low speed and again at high speed, at both steady and varying loads. Again, by specifying control equipment adapted to its duty cycle, some feed drives on machine tools can operate over a very wide range, yet hold a steady speed at any point within their range. If the application involves a group of motors, often it's more convenient and economical to put all control equipment for the motors in one grouped motor control location, such as in this sugar factory. This is often true in hazardous locations like refineries, too, where it may be more expensive to provide special control enclosures for each unit located near a motor. All control is located in a pressurized room or away from the danger area. When the control equipment needed is determined, the final step is to determine the mechanical design features required for both motor and control. In order to ensure long motor life and safety, it's important that the motor enclosure best suited for the job is used. Among those most commonly needed are the drip-proof, splash-proof, totally enclosed, and explosion-proof. The drip-proof type is the kind used where surrounding conditions are good. This type gives adequate protection against falling objects or dripping liquids. One of the enclosed types, on the other hand, is often necessary for extremely dusty or dirty locations or for hazardous atmospheres. Through less maintenance and greater safety, such enclosed types often can save the initial extra cost in the first year of operation alone. When the motor and control are close together, the control always should have the same protective enclosure as the motor. Just as important as the enclosure is the location of a motor and its care during use. By placing these paper mill motors on stilts, they almost certainly will last longer because they're away from the danger of splashing liquids. Again, mounting this motor off the floor helps protect it from dirt and from being hit by moving machinery. Even though this totally enclosed motor is designed to keep out dirt and oil, better results and longer life could be expected if it were cleaned up. The motor mounting must always be considered, too, and for most jobs, the foot-mounted type is entirely adequate. By rotating the end shields, this same motor can be mounted on either the ceiling or sidewall. Where a machine has a vertical shaft, as this cooling pump does, then a vertical motor mounting is used. Quite often, machinery manufacturers make use of face-mounted or flange-mounted motors for mounting the machine directly on the motor or mounting the motor on the machine. Occasionally, where shock loads and rapid reversing duty are encountered, such as on electric cranes or in steel mill operations, motors specially built for these heavy jobs are needed. Generally, these conditions can be met by motors with standard mill-type construction, which includes a heavy-duty frame and a much heavier shaft than on general-purpose motors. Usually, mill-type motors are needed for special-purpose applications such as this winch, and motor requirements are determined by the motor and machinery manufacturer. Thus far, from our review of motor selection, you can see that different applications require a great many types and sizes of motors, ranging from the giant motors which power this wind tunnel to the motor in a small workshop, so light you can pick it up with one hand, yet performing its job easily, efficiently, and economically. Though the range of applications is great, in 9 cases out of 10, selecting the right motor for any job is easy if these 5 basic steps are kept in mind. 1. Study the driven machine. Determine its purpose, its load and speed requirements, its duty cycle, and the product or process involved. 2. Determine the motor horsepower. This usually is done through mechanical formulas, experience formulas, a combination of the two, or through trial or testing. 3. Determine the electrical characteristics. It's usually wise to check the electric utility on the capacity of the supply line and on the voltage, phase, and frequency available. When these facts are known, then a check can be made to see if a standard motor can be selected for operation on the power available. 4. Determine the control equipment. Every motor selected requires some control, whether merely to start and stop the motor, for protection of motor, machine, and operator, or to get a wider operating range for the driven machine. Finally, determine the mechanical design features needed for the job. Enclosure and mounting requirements should be checked, and construction features necessary for the job specified. Just 5 simple steps in motor selection, yet they're of great importance in the selection of motors which serve you faithfully, both today and through the years to come.